What happens when the very defenses engineered to protect our networks, things like randomized memory, stack canaries, execution prevention, what happens when those become the exact stepping stones an attacker uses to achieve remote execution?
Right. Yeah.
I mean, take a second to really think about that because we spend, what, millions on security infrastructure, layered defenses, hardware mitigations, these massive compliance audits, and yet, like, the architecture itself is routinely weaponized against us.
It is, it's the ultimate irony of information security, isn't it? You spend years building this seemingly impenetrable wall, and the attacker doesn't even bother trying to break it down. They use the bricks you provided to build a staircase right over it.
Exactly. And this isn't just, theoretical whiteboard cryptography that we're talking about here. This question is highly, highly relevant today.
Oh, absolutely.
Look at the massive paradigm-shifting situations documented in the recent research we've been looking at. I mean, we are still dealing with the lingering ghost of WannaCry in unpatched legacy environments.
Still. Even now.
Yeah. We're still feeling the regulatory and financial aftershocks of the Equifax data breach. And frankly, I don't even want to think about the absolute chaos of Log4 show.
Yeah, that was a nightmare.
It really was. But these aren't just historical events to read about in some certification textbook. They are active blueprints for modern remote code execution.
Right. And for you listening, whether you're like a cloud architect designing environments or a SOC analyst triaging alerts at 2 a.m. or an auditor reviewing compliance, understanding these blueprints is no longer optional. It just isn't.
No, it's table stakes.
You have to understand the mechanics underneath the hood. Because I promise you the attackers certainly do.
Well said. So today we are taking a highly technical deep dive into the mechanics of remote code execution. We're going to break down how attackers bypass hardware, OS, and compiler-level mitigations, and really dissect the architecture of some of the most devastating RCE vulnerabilities in recent history. Welcome to the deep dive.
It's a massive topic, but a vital one. I think we're going to have a lot of fun unpacking this, even if it is a bit terrifying to look at closely.
Oh, absolutely terrifying. But I have to admit, looking at the sheer complexity of some of these exploit chains, it makes you wonder how any of our systems stay online at all. Like it feels like a minor miracle sometimes.
It really does.
Yeah.
Because when you strip away the abstraction layers, the sleek UIs, the high-level frameworks, it all just comes down to a fundamental architectural flaw in how computers have been designed since the very beginning.
All right, let's start right there. Let's start at the very foundation of execution, which is memory corruption. Now, just to make sure everyone is on the exact same page, we need to clearly differentiate between arbitrary code execution, which is ACE, and remote code execution, or RCE.
Yeah, those get thrown around interchangeably a lot in, like, vendor marketing, but they really aren't the same thing at all.
Right. So break that down for us.
So arbitrary code execution is the broader category. It just means an attacker has found a way to run commands of their choosing on a target system. But they might need physical access to the machine to do it, or they might need to trick a user into running a local script.
Like plugging in a malicious USB drive.
Exactly. Remote code execution, though, -RCE, specifically describes an execution vulnerability that is exposed across a network or a public internet boundary. RCE is the holy grail.
Because you don't need to be in the building.
Right. An attacker doesn't need physical access. They don't need a prior foothold or stolen credentials. They just send specifically crafted packets over the wire, and suddenly they own your server.
And the classic way to achieve that, the granddaddy of them all, is the stack-based buffer overflow.
Oh yeah, the classic.
This concept goes back 30 years, back to the Morris worm and the old Frack magazine articles. But it's still breaking systems today. And to understand why it works, we really need to look at how the x86-64 architecture handles memory. Specifically, we need to talk about the function stack frame.
The function stack frame.
Right. And just as a quick host note here for you listening, in case you're a little rusty on your C programming, think of the function stack frame, or FSF, as the temporary memory space that gets allocated whenever a procedure call is made. It holds the function's local variables, its parameters, and crucially, the return address, which tells the CPU where to go back to once the function finishes its job.
Exactly. And the layout of this memory space is precisely where the vulnerability lies. Imagine memory as this, massive vertical spreadsheet. In architectures like by 86-64, the stack grows downwards toward lower memory addresses.
Okay.
But the local buffers, the arrays or strings you allocate inside that stack, they grow upwards toward higher memory addresses.
Which seems like a massive collision waiting to happen if you aren't careful.
It is a total recipe for disaster.
Yeah.
Think about vulnerable legacy C library functions. Functions like string copy old, strip your gets, or sprint.
The famous ones.
Right? These functions are notorious because they do not perform boundary checking. If you hand struct the string, it has no concept of the size of the destination container. It will just keep writing that string into memory until it hits a null terminator byte.
It just blindly copies. You gave me data, I will write data. So let's break down the anatomy of a stack smashing attack. Let's say a developer allocates a 64-byte buffer to hold a user's name during an authentication handshake. What actually happens at the memory level when an attacker feeds an oversized string into that buffer, say an 80-character payload of just the letter A?
Well, it's simple physics, really, in a digital sense. The first 64 A's fill up the allocated buffer perfectly. But because Straka has no boundary check, the program doesn't stop. It just keeps writing the 65th A, the 66th A, right past the end of the intended buffer.
Spilling over.
Exactly. And remember what sits right above that buffer in the function stack frame? The saved base pointer, which helps manage the stack, and right after that, the saved return address.
Ah, the roadmap for the CPU.
Right. The attacker's ultimate objective is to overwrite that saved function return address. So they don't just send random garbage. They carefully craft that 80-byte payload. The first part is just padding filler to exhaust the 64-byte buffer. The next few bytes overwrite the base pointer.
All right, making room.
But those final 8 bytes, those are perfectly calculated to align exactly over the return address. And they don't overwrite it with A's. They overwrite it with a specific memory pointer that points directly to injected malicious code, often called shell code, that they've hidden inside that initial padding block.
And generating that shell code isn't even the hard part anymore, right? Like, attackers can just use off-the-shelf frameworks to do that.
Oh, very easily.
Huh.
A simple command in a framework like Metasploit, something like Svenom targeting a Windows shell bind TCP payload, will just spit out the exact byte sequence needed to open a port and serve up a reverse shell. Yeah, the attacker just drops that compiled byte sequence into their payload padding. So when the vulnerable function finally finishes executing, the CPU looks at the function stat frame to figure out what to do next. It reads the return address, but instead of returning to the legitimate program flow, it reads the attacker's injected pointer and jumps straight into the shellcode. Game over.
Wait, hold on. Are you saying the system just blindly trusts whatever address is sitting there?
Yeah.
Like, it doesn't do a sanity check to verify that it's returning to the actual compiled program code?
Historically, absolutely yes.
Okay.
The CPU is incredibly literal. It just does exactly what it's told. It reads a memory address off the stack, sets the instruction pointer, the RIP register in 64-bit architecture to that location, and starts executing whatever it finds.
That's okay. I've got an analogy for this. It's like a security guard handing a visitor a blank badge and letting them write their own access level before walking into the server room.
That is exactly what it's like.
Just here's a Sharpie, have at it.
Right. And it all stems from a fundamental trust issue baked into the von Neumann architecture. In a von Neumann system, code and data share the exact same memory space. The CPU cannot inherently distinguish between a memory address that holds legitimate compiled program instructions and a memory address that holds a user's text input. It's all just ones and zeros to the processor.
But obviously, since this vulnerability is literally decades old, defenders didn't just sit on their hands. We didn't just accept that any Strucky flaw meant instant system compromise. They built countermeasures. Which brings us to the hardware's response to this problem.
Right. And this is where the cat and mouse game of information security really starts to escalate.
Yeah.
Hardware manufacturers realized pretty quickly that they couldn't rely on software developers to always write memory-save C code. People make mistakes, deadlines happen, so the hardware layer had to step in and enforce boundaries.
Looking at the research, there were a few early hardware-level mitigations designed to stop this. Things like SmashGuard, which implemented a hardware-backed shadow stack. Basically, the CPU kept a secret secondary copy of the return addresses, and if the main stack didn't match the shadow stack upon return, it would halt.
Right, that was one approach.
Or SRAS, the secure return address stack. There was even something called XOM execute-only memory, which used cryptographic keys to compartmentalize different memory regions.
Those were definitely innovative for their time, but they often incurred really heavy performance penalties or required massive architectural overhauls to work.
Makes sense.
The mitigation that truly changed the landscape, the one that forced attackers to completely rethink their entire strategy, was the no execute bit, or the NX bit.
Oh, right.
AMD introduced it as the NX bit in their 64-bit processors, and Intel quickly adopted it, calling it the execute disable, or XD bit.
So how exactly does a single bit solve a fundamental architectural flaw?
It directly addresses that von Neumann blind spot we just talked about. It adds a new entry to the page table that the memory management unit uses. Specifically, it uses bit 63 in 64-bit mode. This single bit allows the operating system to tag a page of memory with specific permissions.
Okay.
It can mark memory as readable and writable, but not executable.
So RW but not X.
Precisely. Think about it. The stack and the heap exist to store user data, right? Variables, strings, arrays. There is zero legitimate reason for program instructions to be executing out of the stack. So the OS looks at the stack and the heap and sets the NX bit to 1.
So it flags it.
Right. Now let's replay our buffer overflow attack. The attacker successfully overflows the buffer. They inject their EMP's Venom shellcode into the stack. They successfully overwrite the return address. But the moment the CPU jumps to that address on the stack and tries to execute the very first instruction of the shellcode, the hardware intervenes.
But sees the NX bit flag.
Exactly. The memory management unit throws a hardware exception. It essentially says, hey, this memory region is flagged for data only. You are not allowed to run code here. The process immediately crashes with a segmentation fault, but, and this is the critical part, the system isn't compromised. The shell code never executes.
That sounds foolproof. I mean, if you can't run injected code, how do you get remote code execution? The attackers didn't just give up and find a different career path, did they?
Not even close. This is the defining characteristic of this field. When you take away an attacker's ability to inject new code, they realize they don't actually need to. They just use the code that is already sitting there in memory.
Reusing what's there.
Exactly. This marks the massive historical shift from code injection attacks to code reuse attacks.
Code reuse. Okay, let's unpack this because this is where the engineering gets fascinating. The evolution here started with something called return to lib.
Right. Every standard C program on a Linux or Unix system dynamically links to the standard C library, which is known as lib. It's the library that provides basic functions like print, malloc, read, and write.
The building blocks.
Yeah, exactly. And crucially, lib contains all sorts of incredibly powerful, fully executable functions. The most dangerous one for our purposes is system, which basically takes a string and executes it as an OS-level shell command.
Ah, so in a return to lib attack, the attacker completely abandons the idea of injecting their own shellcode on the stack. Instead, they overwrite the return address to point directly to the legitimate system function that already lives inside lib, and they just pass it a string like binge to open a terminal.
Exactly. The memory page holding lib is explicitly marked as executable, so the NX bit doesn't complain at all. The CPU jumps to system, executes it, and the attacker gets their shell.
But return to lib isn't a silver bullet for attackers anymore, especially on modern systems. The research shows it struggles heavily on 64-bit architectures. Why is that transition from 32-bit to 64-bit such a hurdle for this specific attack?
It comes down to the calling conventions, the rules governing how functions pass arguments to one another. In the old 32-bit by 86 architecture, the discrete syntactical calling convention was standard. When you called a function, you literally pushed its arguments directly onto the stack.
Right.
So an attacker could build a payload where they just wrote the string binge onto the stack, pointed the return address to the system, and when system looked at the stack for its argument, it found exactly what the attacker wanted. It worked beautifully.
But 64-bit changed the rules.
Very drastically. In the 64-bit system AMD 64 ABI, which is like the standard calling convention used by Linux and macOS, the first 6 integer or pointer arguments are passed via the CPU registers, not the stack.
Okay.
Specifically, the very first argument a function takes goes into the RDI register. The second goes into RSI, the third into RDX, and so on.
Oh, I see the massive problem there. A buffer overflow only gives the attacker control over memory, the stack. It doesn't let them directly manipulate the CPU registers.
Right.
So you can smash the stack all day long, but you can't easily put the pointer to the binge string into the RDI register, which is where system is going to be looking for it. Plus, if you rely entirely on libic functions to chain things together, you often run into issues with NLL bytes prematurely terminating your payload strings, right?
Exactly.
Yeah.
The strike function stops copying as soon as it sees a 000 byte. Memory addresses in 64-bit space often contain NLL bytes, so trying to write those addresses onto the stack usually breaks the payload.
So return to lib hit a massive wall on 64-bit systems. But that wall led directly to the creation of one of the most elegant, terrifying exploitation techniques ever invented, return-oriented programming, or ROP.
ROP chains.
Yeah, ROP chains. This is the concept that always breaks my brain a little bit. Explain how ROP bypasses the NX bit, solves the 64-bit register problem, and achieves RCE.
Think of ROP like building a ransom note by cutting individual letters and words out of a magazine. The magazine in this scenario is the program's existing executable memory, the application itself, and all of its loaded libraries, like lib.
Okay, I like that analogy.
The attacker uses automated tools to scan this massive block of executable memory, looking for tiny snippets of machine code that end in a return instruction. These snippets are called gadgets.
So a gadget might literally just be one or two assembly instructions immediately followed by a return.
Precisely. And because these snippets are part of the legitimate compiled program, they reside in memory pages that are marked as executable. The NX bit is perfectly happy to let them run. For example, an incredibly common and useful gadget is simply the instruction pop RDI fret.
And pop, for those listening who might need a refresher, is the assembly instruction that takes whatever value is currently sitting at the very top of the stack and moves it into a specified register. In this case, the RDI register.
Bingo. So let's walk through the exact methodology. The attacker uses a debugger or an exploit development tool, something like a GDB-PETA or Wrapper. They scan the target binary and find the exact memory address of a pop RDI rec gadget.
Got it.
They also search memory to find the address of the string bench, which usually exists somewhere in libc anyway, and they find the address of the system function itself.
And then they stitch them together into a chain.
Right. They execute the buffer overflow to smash the stack, but their payload doesn't contain any executable code. It is entirely a sequence of memory addresses. The very first address they overwrite the saved return pointer with is the address of that pop arite red gadget.
Okay.
Immediately following that address on the stack, they place the address of the binge string. And following that, they place the address of the system function.
Let me make sure I'm visualizing this perfectly for you listening, because the choreography here is stunning. The vulnerable function finishes its legitimate work. It hits its own return instruction. The CPU looks at the stack, pops off the first address the attacker injected, which sends the instruction pointer directly to our gadget. Pop arite ret.
Correct. Now the CPU executes the first instruction of the gadget, pop RDI. This tells the CPU to take the next item off the top of the stack and put it into the RDI register. Well, the attacker carefully set up the stack so that the next item is the memory address pointing to the binge string.
Boom. The argument is officially loaded into the exact register the 64-bit calling convention requires.
Exactly. The pop instruction completes. Then the gadget executes its final instruction. And it returns.
Yep.
The CPU looks at the stack again to see where to return to. It pops the next address off the stack, which the attacker set as the system function. The CPU jumps to system. System looks in the RDI register for its argument, finds the pointer to binge, and executes it.
You get a remote, interactive shell, and you achieved it without ever executing a single byte of newly injected code. You just played the program's own compiled executable instructions against itself like playing chords on a piano.
Yeah.
That is both brilliant and terrifying.
It is a masterclass in exploiting state machines. But there is a massive catch to all this.
Nope.
If we connect this back to the real world, for an ROP chain to actually execute successfully, the attacker needs to know exactly where these gadgets live in memory. They need precise, hard-coded memory addresses to build that payload stack.
Because if they're guessing, the chain breaks.
Right. If libc loads into a different memory space, or if the gadget addresses change by even a single byte, the chain breaks. The CPU jumps into garbage data, throws an illegal instruction exception, and the process just crashes.
Which perfectly explains why operating system designers introduced the next major shield in this arms race. They knew that fixed, predictable memory addresses were a massive liability. They had to make the memory landscape a moving target.
Right. Enter Address Space Layout Randomization, or ASLR. ASLR was a complete game changer.
It randomized everything.
Yeah, it takes the base addresses of the major memory regions, so the stack, the heap, and shared libraries like libc and rent, randomizes their starting locations every single time the program is loaded into memory by the OS kernel.
So if you reboot the server, or even just restart the service, yesterday the system function was at address A, but today it's at address B.
Exactly. The attacker's painstakingly crafted ROP chain points to where the pop buddy gadget used to be. But today, that address just holds random data. The exploit fails, The program seg faults, and the intrusion detection system probably lights up from the crash logs.
Now, older systems didn't implement this perfectly, right? There are entropy limitations with ASLR depending on the architecture. I think the research mentioned 32-bit systems had a hard time with this.
Oh, absolutely. On older 32-bit by 86 systems, ASLR was actually surprisingly weak. Because of how 32-bit memory is mapped and the need to keep certain page alignments, the OS only has about 16 bits of entropy available for randomization.
Which means what in practice?
That means there are only about 65,000 possible starting addresses for lib.
65,000 sounds like a lot to a human, but to a computer over a network.
It's nothing. An attacker can write a script to literally just brute force the address space. They just keep throwing the exploit with slightly shifted addresses. Even over a network, they can usually guess the correct random shift within a few minutes.
Wow.
But on modern 64-bit systems, the address space is vast. You have roughly 40 bits of entropy. Brute forcing, that is mathematically unfeasible. You would crash the target server millions of times, creating a massive amount of noise, and you still might not guess it before the server admin notices and blocks your IP.
So ASLR, combined with a 64-bit architecture, stops ROP dead in its tracks.
In theory, yes. In practice, attackers adapted yet again. They realized that brute forcing is for amateurs. They don't need to guess the randomization shift if they can figure out a way to ask the program to just tell them what it is.
And this introduces the concept of an information leak. Okay, an information leak. To explain how this works, we need to dive into how Linux programs handle shared libraries. We need to do a quick host note here and talk about two critical structures: the PLT, or procedure linkage table, and the GOT, or global offset table.
Yes, these are fundamental to understanding the bypass. Think of the PIT and the GOT as dynamic mapping directories that resolve external function calls at runtime. When a developer writes a C program and calls a standard library function like puts to print some text at the screen, the compiler actually doesn't know where puts will reside in memory.
Because of ASLR.
Right, puts lives in lib. And as we just established, ASLR is going to randomize the location of lib every time the program runs.
So the compiler can't hardcode a jump to puts. It has to leave a placeholder.
Exactly.
Yeah.
Instead of calling puts directly, the compiler inserts a call to a small stub of code in the PLT. Let's call it puts at PLT. This PLT stub looks up a specific entry in the global offset table, or GOT. Now, the very first time puts is called, the GOT entry doesn't have the real address yet. Instead, it points back into a resolver function built into the dynamic linker.
This is called lazy binding, right? The system doesn't bother looking up the address of puts until the program actually needs to use it, which saves startup time.
Right, lazy binding. The dynamic linker takes over, goes out and finds the live randomized memory address of puts inside the loaded lib, and then it writes that actual address back into the GOT.
Okay.
So the next time the program calls puts that PLT, the GOT has the real address, and execution flows directly to the function without the overhead of the linker.
It's a very efficient system for performance.
It is. But from a security perspective, this mechanism is the Achilles heel of ASLR. Because while libc is heavily randomized by ASLR, the PLT and the GOT themselves reside in the .plt and GOT sections of the main executable. And traditionally, the main executable is not randomized. It loads at a fixed, predictable base address every single time.
Ah, I see where this is going. So the attacker doesn't know where libc is, but they know exactly 100% where the PLT and the GOT are located in memory.
Yes. And the GOT contains the actual live ASLR randomized memory addresses of any functions that have already been resolved. So the exploit path works like this. The attacker builds a tiny stage 1 ROP chain. Because the PLT is at a fixed location, they can reliably jump to the puts at PEL stub.
Okay.
And for the argument, using that pop-orty gadget we discussed, which they find in the fixed main executable, they pass it the memory address of the GOT entry for a known function, like puts itself.
Wait, let me make sure I'm grasping this. By asking the program to execute puts and feeding it the GOT address as the argument, the attacker is essentially telling the program to print out its own address book.
Precisely. It's a beautiful, elegant, logical loop. The program executes puts, and what does it print? It reads the memory at the GOT address, which contains the raw, live 64-bit memory address of where puts currently resides in the randomized lick. It sends those bytes right back over the network socket to the attacker.
Wow. But wait, libc is huge. Knowing exactly where puts is right now doesn't tell you where system is, does it? You still need system to get your shell.
It actually does tell you.
Really?
Yeah, because ASLR randomizes the base address of the entire library. It shifts the whole thing as a single contiguous block. But the relative distance, the offset between functions inside the library, never ever changes. The distance in bytes between puts and system is completely static for a specific version of lib.
Ugh.
Okay, so the attacker has a local copy of the same libic version the server is running.
Mhm.
They leak the live address of puts. They look at their local copy to see what the static offset of puts is from the base. They subtract that static offset from the leaked live address, and boom. They
That's
have just mathematically calculated the absolute base address of the randomized lib in the target server's memory.
exactly. And once they have the base address, they just add the known static offset for system, and they know exactly where system is. They add the static offset for the binge string, and they know exactly where that is. They have completely mathematically defeated ASLR.
But I see a glaring issue here.
What's that?
If they use their buffer overflow to execute this leak, the exploit has run its course, right? The vulnerable function returns, it executes the ROP chain, it prints the address to the network. But what happens next? If the program finishes and crashes, the next time the service restarts, ASLR will randomize all the addresses all over again. The math they just calculated becomes totally useless. How do they actually use the leaked information to get a shell? That is the crucial pivot point in the exploit. They have to keep the process alive.
How?
They do this by simply continuing the ROP chain. After the gadget that calls puts, the attacker adds one more return address to the chain, the fixed address of start or the main function of the vulnerable program itself.
Oh, that is incredibly sneaky. They redirect execution back to the very beginning of the program.
Yes, the program prints the leaked address and then seamlessly restarts its own execution flow within the exact same process memory space.
So no crash.
No crash. The OS kernel doesn't intervene. ASLR doesn't re-randomize anything because the process never terminated. The attacker reads the leaked address over the network socket, calculates the live address of system, dynamically generates a massive stage 2 ROP payload using those fresh valid addresses, and sends it to the newly restarted vulnerable buffer.
Stage 2 payload deployed. Remote code execution achieved. That is just. It's a masterpiece of engineering. It's weaponized logic, which means defenders had to respond again. If OS-level ASLR isn't enough, because the main executable's fixed addresses allow information leaks, then the compilers themselves had to step in and harden the binaries.
Right. The core issue was that the PLT and GIOT were at fixed locations. So compiler engineers introduced PIE position independent executable.
PIE.
When you compile a binary with PIE enabled, you are applying the ASLR randomization strategy not just to shared libraries, but to the main application binary itself. The .text segment where the code lives, the .plt, the .got all of it, is compiled to use relative addressing, which allows the OS to randomize the entire application space at load time.
So if PIE is enabled, the attacker can't even rely on a fixed puts-at-pelt address to start their leak chain because they don't know where the PLT is either.
Exactly. PIE blinds them completely. And alongside PIE, compiler teams introduced RELRO relocation read-only.
What does that do?
Well, we talked about lazy binding earlier, where the GOT is updated at runtime by the dynamic linker. For that to work, the GOT memory segment obviously has to be marked as writable. Attackers used to exploit that extensively with GOT overwrite attacks.
Right. Instead of building an RP chain, they would just use an arbitrary write vulnerability to overwrite a GOT entry directly, say, changing the pointer for print to point to system. So the next time the program legitimately called print hello, it actually executed system hello.
Yes. RELRO stops that. Full RELRO forces the dynamic linker to completely resolve all shared library functions immediately at startup, before the main program even begins executing. Once every address is resolved and written into the GOT, the OS marks the entire GOT memory segment as read-only.
Oh, nice.
No more lazy binding, no more GOT overwrites. Even if an attacker finds an arbitrary write vulnerability, they can't tamper with the function pointers.
And beyond memory layouts, the compilers also attack the buffer overflow directly. We have to talk about the infamous stack canary, also known as stack guard or SSP. This is such a brilliant, elegant piece of defense. Walk us through the mechanics of the canary.
It's named after the canary in the coal mine, and it serves the exact same purpose, an early warning system for a toxic environment. When the compiler builds the function stack frame, it injects a small routine. It places a randomized 64-bit value, the canary right between the local variables and the saved return address.
So the layout on the stack is the buffer, then the canary, then the saved base pointer, then the return address.
Exactly. Now think about the physics of a standard sequential buffer overflow. To overwrite the return address, the attacker's payload must write past the buffer, through the adjacent memory, to reach the pointer. There is physically no way to jump over the canary. They have to overwrite it with their payload padding.
But the program knows what the canary is supposed to be.
Right. When the function starts, it generates this random canary value and saves a master copy securely in a different memory location, usually in thread local storage, referenced via the FS or GS segment, registers in byte 86. Before the function executes its epilogue and uses the return address, it pauses. It pulls the canary value currently sitting on the stack, and it compares it against the master copy in thread local storage.
If the attacker smashed the stack with A's, the canary on the stack is just a bunch of 0 by 41 bytes. It doesn't match the master copy. The canary is dead.
And if the canary is dead, the program immediately triggers a stack sale exception. It knows a stack smash occurred, and it terminates the process instantly, intentionally crashing before it ever attempts to use the corrupted return address.
And they made these canaries incredibly clever, didn't they? I've seen references in the research to different types like XOR canaries and terminator canaries.
Yes, compiler engineers got very creative. XOR canaries are XORed with the return address itself, meaning the canary value changes depending on the function, making it harder to predict or reuse. But my favorite are terminator canaries.
How do those work?
A terminator canary intentionally forces the random value to contain specific, problematic string terminator characters, like a null byte, 0x00, a carriage return, 000, and an EOF marker like 0xf.
Why intentionally include those specific characters?
Because functions like strikeb or gets the exact functions usually responsible for the buffer overflow, they stop copying data the absolute millisecond they hit a null byte or a new line. So if an attacker somehow learns the canary value and tries to inject a payload that includes the exact terminator canary string to cleanly bypass the check, their own strikeb injection will terminate itself as soon as it hits that first null byte in the canary.
Wow.
It's a built-in trap. They physically cannot inject the rest of their payload.
Okay, so let's summarize the defender's board here. We have PIE randomizing the main executable. We have ASLR randomizing the libraries. We have RLRO locking down the GOT to prevent pointer overwrites. We have the NX bit preventing newly injected code from running. And we have the stack canary acting as a tripwire to catch the initial overflow. It sounds like the defenders finally won the war on memory corruption.
It does sound like a fortress.
But I'm going to use my catchphrase here. Here's where it gets really interesting. Because history shows us that a sophisticated attacker bypasses all of these protections simultaneously.
And they do it by stepping away from buffer overflows entirely and utilizing a different class of vulnerability, a format string vulnerability.
Right. This is a fascinating flaw. This happens when a developer uses a print function like print, but forgets to properly format the input variable, like if they just write print user input instead of print % user input.
Yes, print is an incredibly powerful variable argument function. It parses the string you give it, looking for format specifiers like arrowband for integers, % for hex, or % for long hex.
Right.
When it sees one of those specifiers, it assumes that the developer passed an additional argument to the function, and it reaches onto the stack or into the registers to grab that argument and print it.
But if the user input is the string being parsed, the attacker controls the specifiers.
Exactly. If the attacker supplies input containing format specifiers like %x, %langos,
Right.
%x, perfect, doesn't know that those aren't legitimate variables intended by the developer. It just blindly starts pulling raw data straight off the stack, moving up address by address and printing whatever it finds to the screen.
It effectively becomes an arbitrary memory read primitive.
Precisely. The attacker inputs a massive string of %x specifiers, and suddenly the application is just dumping its entire internal stack memory state back to the attacker over the network.
And this memory dump includes everything. By meticulously analyzing the output and finding the exact stack offsets, the attacker achieves a comprehensive, multi-stage information leak. For example, they might find that the 33rd item on the stack, accessed via $33 LARS, happens to be a saved return address that points back into the main executables.txt segment.
Right. And because they know the static offset of that specific return address from the base of the executable, they subtract it, and boom, they've bypassed PIE. They now know the exact randomized base address of the main executable.
And they can do the same thing to find a pointer into lig to calculate the ASLR base. But the most devastating part is how this defeats the canary. The canary has to be loaded from thread local storage into a CPU register to be checked against the stack. Often that's the RCX register. And guess what else is heavily utilized during a format string function call and often ends up temporarily stored on the stack?
The canary itself. Yes, it's incredible. By simply walking the stack with a format string leak, an attacker can pinpoint the exact offset where the local canary value is stored for that specific function call. They might find that sending $99 literally just prints the highly secure, randomized secret canary value right to the attacker's terminal screen.
If you can read the canary, you can defeat the canary. It's like stealing the vault combination by watching the bank manager dial it in.
Exactly. So the full kill chain looks like this. You use the format string flaw to extract the exact canary value for that thread. In the same request, you extract a PIE pointer and calculate the executable base address. You extract a lib pointer and calculate the ASLR base address. You build an ROP chain using your newly calculated, perfectly valid memory addresses.
Okay.
And then you trigger the actual buffer overflow vulnerability. But this time, when your padding reaches the canary, you cleanly overwrite the canary with its own exact leaked value. The function epilogue executes, it checks the canary, it perfectly matches the master copy, the check passes. The CPU pulls your injected ROP chain address, and your exploit executes. Checkmate.
It's an absolute symphony of exploits. It really shows how fragile these systems are. But as we transition to the modern enterprise, we have to acknowledge that all this memory corruption, buffer overflows, stack smashing, ROP chains, this assumes a low-level language like C or C++O, where the developer is manually managing memory pointers. Most enterprise applications today aren't written in C.
No, they're not.
What happens when we move to modern managed environments? Things like Java virtual machines, C# or PHP. You can't just smash the stack in a JVM, right? The garbage collector and the runtime environment manage memory allocation for you.
Right. Memory corruption is incredibly difficult in a managed runtime. Buffer overflows are practically non-existent in safe, pure Java code. But attackers didn't just pack up and go home, they just moved their focus up the abstraction layer. If they can't corrupt the memory directly, they corrupt the logic of the application itself.
Ah, okay.
This brings us to high-level havoc, and specifically, the terrifying world of insecure deserialization.
Okay, we need to clearly define serialization and deserialization for you listening, because this is the foundation of modern API and web service communication. In these managed environments, you are constantly dealing with complex objects. A Java object isn't just a simple string, it's a class instance that has state, it has internal properties, it has arrays, it might even have active network connections or file handles. You physically cannot easily send a live, multi-dimensional Java object over an HTTP network API to another server.
No, you have to serialize it. Serialization is a process of taking that complex in-memory object and flattening it down into a linear sequential stream of bytes, or, depending on the framework, maybe flattening it into JSON or XML. It's like taking a complex Lego castle, breaking it down into individual bricks, and writing out a list of instructions on how it was put together so you can mail it in a flat box.
And deserialization is the receiving server unpacking that box and thawing the object out. The receiving server takes that byte stream and reconstitutes it back into an active, living memory object in its own JVM.
And that concept of reconstituting it, often done blindly, is the root of the vulnerability. Insecure deserialization occurs when an application takes an untrusted byte stream from a user. Maybe it's a base64 encoded session cookie or an XML payload in an API request, and deserializes it into an object without strictly verifying its contents or its class type first.
Which introduces a concept we need to define carefully. We talked about gadgets earlier when we were discussing ROP chains, snippets of assembly code. But as a host note here, in the context of deserialization, we have something called gadget chains, which are completely different. Deserialization gadgets are sequences of legitimate existing classes, often found in third-party dependencies, that an attacker manipulates to execute unintended commands during the deserialization process.
Exactly. In an ROP chain, we were chaining together low-level machine code instructions. In a deserialization exploit, we are chaining together entire high-level Java classes. This methodology is known as property-oriented programming, or POP chains, and tools like isoserial were developed to automate the incredibly complex process of discovering and building these class chains.
Walk us through the anatomy of a deserialization chain. How does simply unpacking a data structure lead to remote code execution?
It relies on the lifecycle hooks of the JVM. We can break an exploit chain into 3 distinct steps. Step 1 is the kickoff gadget. When the JVM deserializes an object, it doesn't just passively load data, it often automatically invokes specific magic methods to handle the complex reconstruction of the object's state. In Java, a very common magic method is readObject.
So if a class has a readObject method defined, the JVM will automatically execute the code inside that method the moment it tries to deserialize an instance of that class.
Precisely. The attacker searches the application's class path, which includes all of its libraries and dependencies, looking for a class that implements readObject and does something potentially dangerous inside it, like Maybe it triggers a reflective method call, or it dynamically instantiates a property based on the incoming serialized data. The crucial part is that this kickoff gadget executes automatically, merely by the act of the server reading the byte stream. No user interaction is required.
Just parsing the data pulls the trigger?
Exactly. That kickoff gadget then routes execution flow to step 2. The intermediate gadgets. These are basically wrappers or proxies. They take the initial execution sparked by read object and route it in unexpected ways. For example, researchers found that certain classes in the Groovy library, like method closure, could be manipulated. The attacker carefully crafts the serialized properties of these intermediate classes, so that instead of doing their normal job, they pass the execution flow along to the final stage.
Step 3. The sync gadget.
Right. The sync gadget is the final deadly class in the chain that actually executes as the system command. A classic example in the Java ecosystem is java.lang process builder, which is designed to run OS commands. By the time the execution flow passes from the kickoff gadget through the intermediate wrappers and finally reaches the sync gadget, the attacker has perfectly aligned the internal properties in the serialized stream so that process builder is fed the exact string needed to pop a reverse shell.
I love this concept. It's like receiving a flat-pack furniture box in the mail. The instructions and pieces are totally legitimate. They're just standard IKEA parts, or in this case, standard trusted Java libraries. But because the receiver blindly follows the assembly steps in the exact order provided without stepping back to look at the big picture, they accidentally assemble a Trojan horse right in their living room.
That is a fantastic analogy. They are weaponizing the application's own legitimate trusted dependencies against it. And what's truly fascinating and terrifying for developers is that the developer of the vulnerable application might have written perfectly secure code. Their business logic is flawless. The vulnerabilities actually exist in the complex interplay of third-party libraries, like Apache Commons collections or the Spring Framework or Jackson. They just happen to be sitting on their class path to provide utility functions.
And these aren't just theoretical exercises in a lab, right? These exact mechanics, memory corruption, and high-level logic flaws fueled the largest cyber crises of the last decade. Let's look at the real-world applications. Let's break down the taxonomy of modern RCE, utilizing the case studies from the research that really defined this era.
We can categorize the primary vectors of modern RCE into 3 main buckets: memory corruption at the kernel level, web framework exploits, and runtime or scripting exploits.
Let's start with the heavy hitter. Case study 1, memory corruption at the kernel level. The infamous Eternal Blue vulnerability, CVE 2017-0144.
Right, this is the big one. This was the highly classified exploit developed by the NSA, which was subsequently stolen and leaked to the public by the Shadow Broker Group. It targeted a vulnerability in the Windows SMBv1 protocol, specifically inside the srv.sys driver.
SMBv1 is the old server message block protocol used for file sharing in Windows networks, and this exploit is a classic, deeply complex memory corruption flaw. The technical details point to an integer underflow inside a specific function, srvos2 fielist size don't. What exactly is happening in that function?
SMBv1 has a feature that allows clients to send extended attributes with their file requests, specifically OS2 FEA lists. When the srvdsys kernel driver receives one of these lists, it has to calculate how much memory to allocate in the kernel pool to process all those attributes. To do this, it takes the total size of the list and subtracts a certain offset to determine the required buffer size.
Okay, basic math.
But it's basic math implemented in C using fixed-size variables like a dword. If an attacker crafts a malformed packet where the internal sizing variables are intentionally manipulated, that subtraction operation can result in a negative number.
Oh, I see.
But because the variable is an unsigned integer, it can't be negative. So it wraps around to the absolute maximum value, which is 0 like FFFFFFFF, or roughly 4 gigabytes. This is an integer underflow.
Ah, so my math is completely broken.
Completely. The driver gets confused by the massive number during a subsequent size validation check. It ends up allocating a very small buffer in memory, but then it attempts to copy a massive amount of the attacker-controlled FEA data into it.
So we have a massive buffer overflow. But crucially, this isn't happening in a user mode application like a web browser. This is happening right inside the OS kernel.
Yes. And achieving reliable RCE in the kernel requires extreme precision. If you crash the kernel, you get a blue screen of death, not a shell. So the attacker uses an incredibly sophisticated technique called heap grooming in the non-paged pool of the kernel memory.
Let's pause and explain that. The non-paged pool is an area of system memory that is guaranteed to always be held in physical RAM. The OS will never page it out to the hard drive because critical system drivers need immediate access to it.
Exactly. So the attacker sends a flurry of highly specific SMB packets before they even launch the exploit. They are essentially playing a game of Tetris with the kernel memory manager. They force the kernel to allocate and free specific blocks of memory in the non-page pool to arrange the memory landscape perfectly. They want to ensure that when they trigger the vulnerability and their buffer overflows, it overflows into a very specific, contiguous block of memory right next to it.
They're carefully placing the explosive charge. And what structure are they targeting with the overflow?
They want to overwrite a specific kernel structure called the SRVNet connection struct. Specifically, they overwrite the servnet's receive complete function pointer.
So when the kernel tries to process the network connection completion, it looks for that function pointer, but instead it finds the attacker's injected pointer.
Bingo. It jumps to the attacker's injected shellcode. Because this is happening in kernel space ring 0, the shellcode executes with NT authority system privileges, the highest possible access level. It completely bypasses all user mode, OS restrictions, UAC, everything.
And what did the NSA's shellcode actually do once it had ring zeal execution?
It installed a persistent backdoor called double pulsar. And it did it using a highly stealthy technique called a SysCenter hook, intercepting system calls before they even reached the core kernel dispatcher. Once double pulsar was installed, the attacker had persistent, unauthenticated kernel-level remote code execution on demand.
Which is exactly what made it so devastatingly wormable. It required zero user interaction, no phishing emails, no clicking links, just an open SMB port. It's why Eternal Blue was the engine behind WannaCry, which crippled hospitals worldwide. It powered NotPetya, which caused billions of dollars in shipping logistics damage. It even powered the Indexinus crypto mining worm.
It's a textbook example of how a single mathematical error, an integer cast in C code, could literally shut down global supply chains.
Incredible. All right, let's pivot. Case study 2. Web framework exploits. Let's talk about Apache Struts, CVE 2017-5638, which is the vulnerability that led to the devastating Equifax breach.
This is a fundamentally different type of RCE. We aren't dealing with memory corruption, buffer overflows, or NX bits here. It's a semantic flaw. It's a logic flaw in how the framework processes data. Apache Struts is a massive, widely used enterprise Java web framework. The flaw existed deep within the Jakarta multipart parser, which is the component responsible for handling file uploads from users.
So to trigger this, an attacker sends an HTTP request that simulates a file upload. But they intentionally malform the request. They send an invalid content type header.
Right. The parser tries to read the content type header to figure out how to process the file. It realizes the header is invalid, and it throws an exception. It catches that exception and passes the invalid string to a localized error handling function called localized text util.find text. The goal is just to generate a helpful error message for the system logs, or to display to the user, like, hey, you sent an invalid content type.
And here is the fatal logic flaw. That find text function didn't just passively log the string, it actively evaluated the string before logging it. Specifically, it looked for anything wrapped inside a specific syntax, the $ and curly braces syntax, and evaluated it as an object graph navigation library, or OGNL expression.
Yes. OGNL is an incredibly powerful, dynamic expression language used heavily internally by struts. It can access internal server objects, modify application properties, invoke methods, and, crucially, through Java's Reflection API, it can execute arbitrary Java code.
So the attacker literally just puts a malicious OGNL expression inside the HTTP content type header, wraps it in the syntax, and intentionally sends a broken request to cause the error. The server catches the error, passes the attacker's string to the logger, and the logger happily executes the attacker's code while trying to format the error message.
Exactly. Now, to be fair to the Struts developers, they knew OGNL was dangerous. They had a sandbox in place to prevent OGNL expressions from doing catastrophic things. It had a block list called excluded classes that explicitly blocked access to dangerous classes like java.lang process builder or java.lang runtime.
So how did the attackers get RCE if the sandbox blocked it?
Because the OGNL expression language itself was so powerful that the attacker's payload could modify the sandbox while executing. The payload essentially reached into the OGNL context memory space, cleared out the excluded classes array entirely, effectively turning off the security cameras, and then executed java.lang process builder to pop a shell, all in one single request.
Wow! They weaponized the error handler. And that single HTTP request led to the compromise of 147 million highly sensitive credit records at Equifax.
Because they achieved unauthenticated command line access to the web servers. And because of poor internal network segmentation, those web servers had direct, highly privileged access to the back-end core databases.
Which brings us to the final and perhaps most notorious Case Study 3, Log4Shell, CVE 2021-44228. This is the ultimate example of scripting and runtime exploits using dynamic lookups.
Log4Shell, the absolute shell shock of the modern Java world. Log4j is arguably the most ubiquitous logging library on the planet. Every enterprise app uses it. And much like the struts vulnerability we just discussed, Log4j had a convenience feature called message lookup substitution.
So developers could log dynamic variables. They could write a log statement like user logged in from nv OSA name, and Log4j would automatically resolve the environment variable and print the actual host name in the log file.
Right, it was meant to make logs more readable. But one of the lookup protocols it supported was JNDI, the Java Naming and Directory Interface. JNDI is an API designed to let Java applications look up and load data and objects from external directory services, like an LDIP server or an RMI registry, across a network.
I think anyone who has worked in IT in the last few years knows exactly where this is going. An attacker takes an exploit string, something like netjnd.ldap.malicious-server.com/exploit, and they just spray it. They put it anywhere they think the target application might log it. They put it in the user agent header of an HTTP request. They put it in a username field. They put it in a search query.
Target server receives the request.
Yeah.
The web application, operating perfectly normally, logs the user agent string using Log4j. Log4j's parser sees the syntax. It parses the JNDI command. And because it's designed to resolve these lookups, the server literally reaches out across the internet to the attacker's malicious LDIP server. The LDIP server responds not just with data, but with a compiled remote Java class file. The vulnerable server downloads that class file and executes its static initializer block right there in the application's memory space.
Oh, wait, let me push back on this because there's a technical nuance here. How did this work on newer JVMs? The historical documentation shows that later versions of Java, specifically after 8U191 disabled remote code-based loading by default via the trust URL code-based property, Sun and Oracle recognized years ago that blindly downloading remote code via LDAP was a massive security risk. So a modern JVM shouldn't have executed the downloaded class, right? It should have blocked it.
You are entirely correct.
Yeah.
Modern JVMs block the remote class loading. If the LDAP server tried to send a class file, the JVM threw an exception. But attackers found a terrifying workaround that completely bypassed that restriction.
How?
Instead of trying to force the server to download compiled code, the malicious LDAP server returns a specific JNDI response called a reference. This reference tells the local JVM, hey, I don't have the code you're looking for, but you have a local class factory on your system that can build what I need.
Oh no, they use local classes.
Specifically, they utilized the jabax.naming.spi.objectFactory interface. The LDAP reference points JNDI to a local class that already exists on the server. The most famous example used classes native to Apache Tomcat, specifically org.apache.naming.factory.beanfactory. Because this class already exists locally on the class path, the JVM trusts it completely. The trust URL code-based restriction doesn't apply.
And what does this bean factory do?
It instantiates other classes. The attacker instructs this local, highly trusted bean factory to instantiate another local class, specifically javax.ll.el processor, and they configure it using the payload provided in the LDAP reference. The EL processor class has a method called eval, which is designed to evaluate expression language code.
So they completely bypass the remote code-based restriction by manipulating the server's own local, trusted factory classes to assemble an evaluation engine, and then feeding it malicious code to execute. It's essentially a complex deserialization-style gadget chain, but it's triggered entirely via a simple text log injection.
Exactly. It was an elegant, devastating bypass that forced the entire software industry into a massive panic. Every company on Earth was scrambling to upgrade Log4j and forcefully rip out the JNDLOOKUP class entirely.
So what does this all mean? We've gone from smashing the stack by counting bytes in C to leaking OS memory to defeat mathematical ASLR randomization to exploiting Java deserialization hooks to popping remote shells just by putting a string in a user agent log file.
If we synthesize all of this, from the 1990s to today, the common thread is misplaced trust. From basic buffer overflows to complex JNDI lookups, RCE fundamentally relies on systems trusting untrusted input. The CPU trusts the return address blankly. Printa trusts the format string. The JVM trusts the serialized byte stream to be safe, Log4j trusts the text it's logging.
And as defenders, how do we survive this ecosystem? We can't rewrite every piece of software on Earth. The research points to a few critical defense-in-depth strategies.
First and foremost, you need extreme visibility into your supply chain. Dependency auditing. The concept of software bill of materials, or SBOMs. You physically cannot patch log4j if you don't know it's buried 3 layers deep as a transitive dependency in your vendor's proprietary software. Robust patching life cycles and knowing your attack surface are the absolute baseline.
The documentation also heavily emphasizes network segmentation and web application firewalls.
Absolutely. WAFs are critical. A good WAF can catch those generic OGNL signatures or JNDI payload strings at the network perimeter before they ever reach the vulnerable application parser. And network segmentation is non-negotiable. If a public-facing web server gets compromised via an Apache struts flaw, it should not have direct, unauthenticated access to the core customer databases, which is exactly what exacerbated the Equifax situation. Also, disable legacy protocols. There was zero valid business reason for modern enterprise networks to be running unsegmented, unpatched SMBv1 across the globe when Eternal Blue hit.
And finally, continuous monitoring for anomalous behavior, because you have to assume breach. You might not catch the zero-day exploit payload itself, especially if it's deeply obfuscated, but you can absolutely catch the post-exploitation reverse shell trying to phone home to an unknown IP address.
Exactly. Defense in depth. Assume the mitigations will fail, and plan your architecture accordingly.
This has been an incredible deep journey through the actual mechanics of RCE. Do you have a final provocative thought for our listeners to take away before we sign off today?
I do. Consider this. The sheer complexity of modern software development means we are building systems we barely understand anymore. We are relying on incredibly deep dependency trees, where a single misconfigured string parser in a library written by an unpaid open-source maintainer can grant kernel-level access to an attacker halfway across the globe. Are we engineering ourselves into an undefendable corner as we add more abstraction layers, more dynamic evaluation features to our languages? Are we actually making things safer, or are we just creating vastly more intricate ways for attackers to achieve RCE?
That is a chilling thought, and definitely something to mull over the next time you type npm install or maven build.
For sure.
Thanks for tuning into InfoSec Bytes. Keep exploring our 100+ episodes on information security, AI, cloud, quantum, and cybersecurity incident root cause analysis. Please like, subscribe. We are on various platforms: Spotify, Apple Podcast, YouTube, Amazon Music, and share to stay connected and keep your cyber defenses strong. See you in the next episode. Stay tuned.
Bye, everyone.
Take a hard look at your own infrastructure today. How confident are you really that your third-party logging libraries and API parsers aren't blindly trusting the data they record? Think about it, and we'll catch you next time.